So after grading the first exams for 360, I was clear I needed to take action to try and provide a way to get everybody on board so that we can successfully finish this semester and get ready for 460. At the same time, I finished grading the 460 exam and again had a feeling that my 460 students, some need a little special tender loving care to catch up so we could finish our project and get on with the semester. So I'm really hoping that this walkthrough of my presentation provides you a means to step through, check your understanding against what I think you should have at this point in time. Uh, so I'm hoping everything goes well. If you have questions, please feel free to write an email and ask, and I'll do my best to respond in a timely manner. Right now, though, it was clear to me from the majority of the grades, uh, either you're fighting for time doing other things, or the background 201, 301 really hasn't been as thorough as it should. Um, I really want your education to mean something. I don't want you just to pass through the different classes and graduate really without a good, thorough understanding of this field. So I'm taking the time. I hope you meet me by walking through the videos, slowly looking at each page, consider what I'm saying, and make sure you understand. So the first question I have is, in each of the classes, I post a series of supplemental information, digital stuff, Verilog stuff, some of which I walk through in class, others I don't. And the ones I don't, just because I don't walk through them, I wouldn't think that you would ignore them. You should look at what's posted and kind of get a feel for why I posted it up there. So today I'm going to walk you through a series of presentations that I have, and so I've chosen slides from them. So starting back for the 201 students or the 360 students, one of the problems was for you to draw a simple logic diagram for a Boolean equation. And not everybody could do it, which to me is unthinkable at this point in time. So you should know all of the logic symbols for all the fundamental gates, the and, the or, the not, exclusive or, NAND, nor, even a buffer, as well as you should know the truth table. This stuff should have been clear from 201. You need to make sure you know. So the students that couldn't draw an exclusive OR gate, you should. Then on the right hand side also, at this point in time, you should know the Verilog operators for the different operations. And I'll have more to say about that later, which is now. So first of all, keep in mind that the operators are not just Verilog operators. They are the same as you'll encounter in Java and C. Some of them are applicable, some aren't totally, but the ones I want to address are. So bitwise versus logical. So Boolean or Verilog has two different types of operators. So you can see coming down the left-hand column of the blue page there, bitwise negation, bitwise and, bitwise or, bitwise exclusive or, bitwise exclusive nor. All these are allowing you to perform what I call bit twiddling on bits. Very straightforward. Most of us know exactly what's going on. At the same time, if you go further down, you see logical and logical or. A logical and has two ampersands. A logical or has two bars. The difference is the tools, not only Verilog, but C, Java. When you use a logical operator, it assumes the operands are logical values. So what it will do, it will reduce the operands to be considered either true or false. If the operands are scalar, then intuitively there's no difference between a logical and bitwise operator. If the operands are vectors, there's a big difference, as demonstrated below. The bitwise will twiddle the bits. The logical will reduce the operands to either a true or false and then evaluate it. So what we want to do is we want to make sure we use bitwise for bit operations, logical for logical operations. Now, don't think if your operands are still scalars or 1 bit wide, you can intermix them. It's still not the same. And how is it different is the hierarchy of operations, as you can see on the right hand side, is different. A bitwise operator has a different hierarchy than a logical operator. So just be disciplined. When you're twiddling bits, use the bitwise operators. When you're doing logical operations, use the logical operators. The switching characteristics with the gates, fairly straightforward. This is more addressed to the 360 students. But what I want to make sure is that we all understand that when we're modeling for simulation, we use ideal circuits. So what that means is that when we run the simulator, you can use a gate of any sort. It'll switch immediately once the input switches. But you must keep in mind that in the real world, even we talk about the fact that light takes time to travel, there will be a delay through all the operations that we use, be it an AND gate, an OR gate, or eventually flip-flops. So you need to be able to explain that yes, when we're modeling, I don't use delays, but I know when I have my circuit built, there will be delays. And it turns out without those delays, we could not build the synchronous digital logic circuits that we utilize. Flops are the same. With a flop, what's different is that we have the concept of a clock. And the clock will have a frequency and a period. And I continue to push that I expect you to be able to, in simple terms, move between clock frequencies and clock periods. But it's the clock period that sets up the budget. And the budget means I have to get all my work done in one clock period. So what are the consumers? The consumers are what takes time. So when I look at a representation or an abstraction of a typical digital circuit in the right-hand window, I can see the typical circuit starts with a flop, which is switched on the active edge of the clock. It passes through some combinational cloud, and then it has to arrive at the input of the next flop. And this all has to be done in less than one clock period. So the first time from the clock till it takes the cue to switch is called the time to switch from clock to cue. The combo cloud I just generalize as a propagation delay. And then the third is the setup delay. So again, when we model or simulate and we look at the waveforms, everything happens instantaneously. So on the active edge of the clock, the flop switches, it looks like the cue switches immediately. You need to keep in mind that in reality, and even in the way they model the Verilog for simulation, there will be a delay from the active edge of the clock until the output of the flop switches. So the we think, we write, we get, uh, just in general terms, uh, I'm leaving out the we compute. At those days, a long time ago, you can see I wasn't thinking we compute. But it's still the same thinking process. When we go to capture a digital circuit, the first thing I want you to be able to do is to itemize the ports. And that is the purpose of the top level block diagram under the we think. I know that within that block there's a certain amount of logic. But initially, before I design that logic, I want to say, okay, I just need this. And even when you sketch your circuits, you can use these top level block diagrams to sketch the way the data flows through your system. You can then assign what your control line should be. And then later you do the rewrite where you add the details. And then the we get, we don't really deal with that much, but I can't emphasize enough that when we write our Verilog, we need to keep in mind that the end product of what we're writing is hardware. With Java or with C, you compile your high-level language. What gets generated is machine code, which gets loaded and executed in a computer. It's not the same here. Everything we write is going to get implemented using gates and flops. Now I know here that I'm using a low active reset. That's what I have been using up till now. But on the right, I want to be able to emphasize that when you look at a graphic symbol, you should be able to read and understand the active edges or levels of the inputs. So on the right, on the upper one, you can see the clock runs straight in. That's telling you it's a pause edge clock. If the designer wants to document a little negative edge clock, he'll put a bubble on the input, or should. That bubble tells you that that flop is updated on the negative edge of the clock. Now, without a doubt, we always use the pause edge, but you want to be able to read and understand these logic diagrams. The load is a control signal. Again, no bubble tells you it's high active. And my standing joke here is a bubble looks like a zero. So when you see a bubble on an input or an output, think low, think zero. So the active state of the load input is a 1. Data doesn't really have an active state because it's either up or down, but the reset, in this case, you're seeing it as a low active reset. And by now, everybody knows that in our implementations, we're using high active resets. But the graphic symbols remain the same. You need to be able to read them when you're looking at them. A little more on combinational delays. I just threw this in. Whenever we draw a schematic, we should draw it from left to right. The flow is always from left to right. The transition through the gate or the switching is captured in terms of what's going to happen on the output. So they call the time to propagate from low to high means the time it takes for the output to switch from a 0 to a 1. The time to propagate from H to L, from high to low, is when the output is switching from a 1 to a 0. And the general rule is that it takes longer to switch from low to high than it does from high to low. And that's because it just takes more time to charge the net, to bring that whole net up to what is considered a logic 1. If you look at a scope, and I admit readily this is not a scope, this is just me sketching on a presentation, but it would look something like this. When the inputs switch from low to high, There's a certain propagation delay, then the output switches. Same thing, the input switches from high to low, a certain delay, then the output switches low. There are other considerations that we don't get into. There are parasitic delays, they refer to them as, which is the amount of metal inside the device that's running from our output to the input that we're talking to. And then the number of loads that we have also increases the delay. So for us, we don't really talk too much about that, but in reality, these are all considerations that need to be made when you're considering the timing behavior of digital circuits. And lastly, I just want to chat a little bit here. Considering timing, there's two worlds to keep in mind: the simulated world and the physical world. When we model with an RTL, there's no references to clock other than the pause edge of clock. So we call it register transfer language, or register transfer logic, or register transfer level, you choose. What it's referring to is that our design is moving from register to register on the active edge of the clock. We don't put any other delays in, so we don't model delays in our gates sitting between the flops. The simulation that we run, the goal is to prove the logical correctness, not to prove the proper timing. The confirmation of the proper timing is responsible for another tool called a static timing analysis tool. And that'll be the subject of the last third of 360 this semester. And I want to make sure we're ready for it. So that's why we need to catch up here. Things that vary, speed, voltage, temperature variations contribute. So on the right-hand slide, it's just a reinforcement of what I said a few minutes ago about who are the consumers. And the net result should be a positive margin or a positive slack. And you'll find that different managers, when they are overseeing teams of engineers, will tax the engineers, meaning that they may say, oh, I want you to have a 10% margin. So when you do your timing analysis, even though your clock period is 30 nanoseconds, tell the tools you have 27 and see if it still works. And what they're trying to do is hedge their bets. They want to make sure under all circumstances, temperature, voltage variations, this circuit continues to work properly. Setup and hold are fairly easy to understand. In the analysis that I've been talking about, where we say who the consumers are and how much work we can get done in a clock period, it's only setup that's considered. Hold is not a contribution to what is referred to as worst case analysis. Hold comes in when we're talking about clock skew. And I think I have a slide or two about that, but we'll come back to that. So on the right, we've already talked about it. Make sure you know the active edge of the clock. For us, it always will be pause edge, and the symbol is meant to designate that. Setup shows the period of time before the active edge of the clock. The data must be stable. Hold is the period of time after the active edge of the clock. The data must be stable. Where it comes into play is in the clock skew, which is meant to be diagrammed here. We have two flops, F1, F2, both on the same chip. They could be on different corners of the chip. Both are getting clocked with the same clock. In reality, though, we know that the clock is buffered, so the clock is spread out throughout the design. And where clock skew becomes a problem is when the delay from one clock edge on a flop to the same clock edge on another flop is greater than the data delay between those two flops. What that means is that the data we clock at the second flop is wrong. So this is where hold comes into play. It's more to do with clock skew. We rely on our tools to ensure that we don't have this situation, and we assist the tools by only using the clock trees to clock our flops. This is why I insist only clocks go to clocks. Here, I think you can read this yourself. Nothing new. I'm going through my 201 slides mostly for the 360 students. I feel that there's a hole and I'd like to fill it. So in teaching 201, once I have laid the foundation of combinational logic, the next thing I do is I want to transition to sequential logic. So in my world, when I say combinational, you think gates. When I say sequential, you think clocks or flops. But in the transition period, what I want to talk about is state. State is the ability of a digital circuit to retain a value. So when you refer to a state of the machine, it means all the storage elements, what is their value at that given point in time. So if I have 1,000 flops in my design, the state of the machine at a particular time is identified by the value that's in every flop at that point in time. So before we learn in 201 about flip-flops, we take a moment to learn about latches. So a latch is built using combinational logic. That's why I consider it a part of the combinational world. The difference is we use what's called combinational feedback, which in general use is frowned upon. But specifically what it allows us to do is to design a simple circuit that will retain a value. On the left and the right is the same of the left of the latches slide. It's really the same behavior with the difference the active state of the inputs. With NAND gates, you have low active inputs. With NOR gates, you have high active inputs. So the truth table for the NAND implementation, 0, 0, I say don't do that. XX means just don't do it. We know that when you hold S and R both low, it's going to force Q and Q bar to a 1. But the point is, if you need a latch, don't ever allow your control logic to try and set the Q and the Q bar at the same time. Conversely, since the latch is low active, when the set is low, the reset is high, the output goes to 1. When reset is low, the output goes to 0. And now, when they're both 1, the 2 dashes means no change. Another way to say it is Q sub I plus 1. If Q sub I is the top of the column, Q sub I plus 1, meaning where we're going, is Q sub I. No change. So what we've done is we're storing that state of the latch in the latch. The same is true on the right-hand side with the NOR implementation. Soon as we understand the functionality of the latch, we can then move on to what is referred to as a D-latch. When we draw D latches, they do look similar to a flip-flop, but they are not a flip-flop. They are still combinational logic. The behavior of a D latch we should all have memorized. When the latch is enabled, the output follows the input. When the latch is disabled, the latch will retain the value on D at the time it was disabled. It will latch the D. We may have a reset into a latch. And what I paused for, I wanted to say that this is why we call a latch, a D latch, a transparent latch. And what that means is that when the latch is enabled, what's happening on D passes right through the latch and happens on Q. So you can see that here, and I know that the pointer device doesn't always work. On the timing diagram, when when it's high the first time, it's when the enable is high, the D goes up, the D goes down, Q goes up, Q goes down. But when the latch is disabled, when enable goes low, the value on the input, which is D equal to 0, is retained until the latch is enabled again. For us, we're going to see we don't want latches in our designs, but as a digital designer, it's expected. You know what it is. How do you model it? You model it by what is referred to as inference. I infer a behavior in the way I write my Verilog code. So this is an old slide, so it's a little bit of older. So here I have all three of my inputs in the sensitivity list. Today we would just say always at asterisk. When reset's active, my latch goes to 0. Else, when my enable is a 1, gets D. That's the transparent. As long as the enable's a 1, whatever happens on D shows up on Q. We don't have an else. The else, it tells the tool when you reach that else condition, since I haven't told you what to do, hold the value that was there. The way the tools do that is that they implement a latch on the output. So on the left-hand side, I'm showing you how when you want to model a latch, you would. Remember that you can infer now unwanted latches if you do this in your combinational logic design. What I mean is that if you have an if-else or a case where you haven't specified every particular branch, or if you haven't provided a default assignment at the top of the iterative loop, you will get latches in your design. And it's something the managers don't appreciate. You waste resources and you burn timing, as well as it's just not good form. So understand what a latch is, know how a latch operates, know that there are times in the digital world where a latch is useful, but ensure by your style of writing your Verilog that you don't infer unwanted latches. So when we make the big turn, we're going from combinational to sequential. The combinational y equal to f of x, whatever happens on the inputs, x immediately gets updated to the output. Now we're moving on to flops. Once you understand flops, you can understand registers, counters, shift registers, a bunch of cool stuff that you can now build more and more complicated circuits. So the fundamental building block that we use, and I'll say this again, is the D flip-flop. That's the flop when I draw a flop in class or on my board or on my presentation that I'm using. That's the flop most of the libraries for these devices that we use have. When we want to build a little bit different, we just have to add logic on the input. So we'll see some examples. So first, let's keep in mind how a flip-flop operates. Depending on the way the flop is defined, on the left we see a pause edge triggered flop, on the right a neg edge. So on the left, what that means is it's only when the active edge of the clock occurs the output may switch. Same thing on the right. Now I want to linger here just a moment. Whenever I ask students to draw timing diagrams, inevitably someone will show signals on the output switching randomly, switching in the middle, switching just crazily. Immediately I realize this person does not understand how flip-flops operate. This is why, and we'll see a slide a little bit later, first thing I do when I'm doing this, I take my straight edge, which everybody should carry in their pocket with your pen protector, have a straight edge, pencil, eraser, a pen, and I take out my ruler and I put dotted lines coming down off the active edge of the clock, telling me that's when my outputs switch. If you do that, you won't have some crazy switching in between the active edges of the clock. On the right, just a word about asynchronous reset. Yes, the AISO circuit that we've defined and built synchronizes the release of reset, but still each of the flops have an asynchronous reset. What that means is whenever the reset is active, Q goes to 0 immediately. Now you can define a flip-flop that when reset is active, Q goes to 1. It's still considered the reset state. The difference would be our circuitry expects the output to be a 1 following reset. So two things from this chart. One, everybody should know the only time the output of a flop, so that means a register, a counter, anything that receives a clock, the only time that output switches or may switch is on the active edge of the clock. You are able to convince me that you understand this by the way you respond to my questions on quizzes and exams. Please be careful. Like I said, when you just kind of randomly have your output switching, that tells me you don't have it. And it's too bad because this is a concept that should have been solidified in 201. And there are my lines. Although here I show the output slanting a little bit, it's not necessary. If you like that, if that's easier for you to understand, I recommend go ahead and do it. But that chart demonstrates with a D flop, it's on the active edge of the clock. The value on D is copied to Q. Again, that's a verse you should have memorized. And it should be clear to you whenever you approach this subject. Now on the right, what I'm talking about is, hey, there are different types of flops that you need. So there's a trigger flop that toggles every time. It's set, a JK, which follows a pattern shown in the truth table. Years ago, 74, I think 112 was a dual JK flip-flop. For us, if we want it, we can build it. Who we use mostly are SR flops, and we use them for handshakes. So maybe we'll see that in a little bit. This is just stressing the fact that we have a clock. We use a common clock. The frequency determines the period. And there are timing constraints on our flops that must be met for them to work properly. and that's in particular the setup and hold. Let me mention just for our AISO, same is true there with respect to the reset to the clock. You have to be careful when the reset is deactivated to the flop relative to the active edge of the clock. That's why we have a synchronous release, so we know our resets are turning off just after the active edge of the clock. We then have that entire clock period for our signals to stabilize. On the left is an example of a D flop. Difference today is I don't use the keyword OR in the sensitivity list, and we're using a high active reset. On the right shows, hey, now if I wanted to, I can start defining logic that will have a flop on the output. So I need a multiplexer, but I want the output of my multiplexer to be registered. So you could call it a registered mux. How we do that is in the Verilog, for the two branches, we put the logic. So if select is a 1, the output gets B. If select is a 0, the output gets A. So we don't use, now maybe we do, maybe we don't. We're using a little bit different style, at least in our state machines. But keep in mind, anytime you have a sensitivity list that says pause edge of clock, neg edge of reset, or pause edge of reset, you know the output will have a flop. It does not mean there won't be any combinational logic on the front end. It just means the output will be a flop. And let me say, for our designs, although Pong Chu doesn't practice this, I want to practice this. So in our sensitivity list for sequential circuits, we only have pause edge clock, comma, pause edge reset. Always include a reset so that your flops get initialized during the reset. So I'm going to go a little quicker here. This is just showing a T flop. You can linger here if you want to understand how it operates. The bottom shows the timing analysis for the T flop. Keep in mind the first clock edge, even though the D is a 1, Q does not go to 1. Why? Because reset is still active. It's not until reset is inactive that the output is allowed to follow the input. JK, this is how we build it. The emphasis here is that whenever we want to conditionally set our flops, be it a JK, be it an RS, what we do is we put logic on the data input of the flop. Now, it's that logic then that determines how the flop operates. And what we have here is a flop, when you look at it in the top level abstraction, is a JK flop. And it'll behave as the truth table defines and as the timing diagram shows in the right hand side. Metastability, we've been talking about this a lot, both 460 and 360. I want to make sure that everybody understands what I expect you to know. What is metastability? Metastability is when the output of a flop, and it's important you say flop. It's not just a signal. It's when the output of a flop oscillates and settles in an unpredictable state. Unknown state is not correct. There are only two known states, 0 and 1. The flop will settle in a known state. It will not settle in a predictable state. So from the paper I've got on BeachBoard, these are some clips. The upper left shows a storage scope. Don't be confused. What they've captured is Q and Q bar. Sometimes flops have the Q bar output. That's meant to just show the two outputs. One goes north, one goes south. And it's a storage scope. So it's collecting the different, they may run it 1,000 times and they collect the waveform, and that's how it works. It shows on the upper, sometimes it's settled to a 1. Sometimes it's settled to a 0, but that middle part where it's kind of scattered, the scatter pattern on the scope shot, that is the metastable state. What's exactly going on is subject to debate. It may not be oscillating. They say it floats between active states. Whatever. It's a period of time when the output is not usable. That is the metastable state. That is what we want to stay away from. And what we assert is that if a flop does reach a metastable state, it will settle. By settle, I mean it will either end up as a 0 or 1 in less than 1 clock period. So from the last page of that paper, this is how they deal with metastability. It says digital circuit engineers must determine the metastability characteristics of their circuit. The degree can determine the reliability of the circuit. Ways of limiting metastability include 1 clock, faster flops, decreasing the asynchronous input frequency, using synchronization hardware. So I say there's 2 reasons. The first is bad design. In that case, slow the clock, faster technology, redesign with pipeline. The second is when we must have signals that cross clock domains from a 60 megahertz to 100 megahertz. Here, something is necessary. We need to do that. We know that we will have metastability, but now we have to design around it. That is where the use of the synchronization hardware comes in. The only caveat is we have to be able to sample the incoming signal in the receiving clock domain, and we'll see a slide about that. So I like philosophy. So if everyone in the world had the same internal clock, perhaps there wouldn't be so much misunderstanding. Unfortunately, in our world, everybody has their own clock. So synchronous design, all of that, I'm stating the obvious. Here is another slide, just again emphasizing what causes metastability and how we avoid it. So on the bottom, it shows the metastable state, much less than a clock period. If I switch my input outside the setup and hold window, that's good. If I switch my input inside my setup and hold window, that's bad. It's when our input switches in that window, the output can enter the metastable state. So there's 2 cases. The first case demonstrates a signal too fast. So let me read it. For single pulse signals sourced at a faster frequency may not be sampled by the receiving clock. So what we have is F clock generating F data. It comes and goes. We never see an active edge of the S clock. On the bottom, we have the second case where a slower clock is generating the signal and the fast clock has plenty of edges to capture it. There is a solution to case 1, but I don't want to pollute your minds. So perhaps we can talk about it in the lab sometime. So the simple solution is using the case 2 is we take the signal from the clock domain, and I know it's not slower here, but we make sure that the data input is able to be sampled following the Nyquist sampling, and we allow the output of the first flop to enter a metastable state, but it's the second flop that we utilize, and we assume that the metastability never makes it to the second state, second flop. The recommended approach that I talked about, I documented, let me go through it again, is that the control signal, in this case data ready, that we don't limit it to a particular number of clock edges. What we do is we have a tactile feedback that the receiving clock domain B acknowledges the fact that it has received the data, telling the sending domain A that he can now move on and turn off the data ready. So down below, the timing diagram is meant to show that data ready goes high, the data acknowledge comes. Once the sending guy sees the data acknowledge, he can turn off his ready. Now I may have drawn that improperly. I may have wanted the ready to turn off, then the acknowledge to turn off. Let's look at the next one. But the feedback is a much better approach to handling metastability. So here is a little sketch that I had put together that shows on the bottom half what we have is we have a system that needs to communicate data to another system in a different clock domain. So I say n bits, it could be 8, 16, 32, 64. So what the sending domain will do, it will write the data to the data register, then it sets, and I don't have the set here, it sets the data available. That causes the data available signal to go to the receiving clock domain where he needs to synchronize it. Once he's synchronized it, he can generate a pulse which will come back to acknowledge and knock down the data available. At the same time, it's used to capture the data off the bus. So what is meant to be demonstrated by this diagram is that when you're synchronizing control signals that are controlling the movement of data, you do not need to synchronize the data path. It's only the control path that needs synchronization. What does metastability have to do with reset? This was a topic we covered at the beginning of the class. Let me say reset is an extremely critical signal in the digital design world. In the theme of always being in complete control, the designer needs to know that the state of the machine will be known whenever there is a reset. Reset occurs at power up and whenever there's a catastrophic event that demands the system to start over. When that happens, the proper design of reset ensures the machine always starts up properly. So some systems, I agree, don't require a reset. As we've mentioned in ASIC design, a flop with a reset is more expensive. So it may be prudent to not include a reset. That would be perhaps maybe a camera processing video data. Once the video data starts streaming, it just initializes all the flops to a known value. But for us, in our classes, we will always use reset. And the problem historically was the release of reset was controlled by a manual switch or an RC circuit on the board that had no timing relationship to the clock inside of the design. So to resolve that, the asynchronous in, synchronous out circuit was defined. In this case, what happens is when the reset in goes high, the reset out goes high. When the reset in goes low, following the first clock edge, the first flop gets set. It may exhibit metastability because there's no timing relationship between the release of that reset and the clock. If it does, it'll settle though in one clock period, in less than one clock period. So the second flop will be clean. When it goes high, the reset out goes low. And what we're doing is synchronously releasing the reset to our circuit. On our exam, I asked you to draw the circuit. Many of you couldn't. When you have an assignment, don't clone a design and feel like you've achieved your ends. You are cheating yourself if you don't take the time to understand not only how we define the circuit in Verilog, how it will be implemented in hardware, but why we're implementing it. That would be a good education. And the last note here is keep in mind, if you have a design that has multiple clock domains, you must have a circuit like this for each clock domain. Debounce, I'm going to move pretty quick through here. Keep in mind, debounce is different than metastability. Metastability, we're talking tens of nanoseconds. Debounce, we're talking tens of milliseconds. So it's different. The upper left shows exactly what we're talking about. When the switch moves from a 0 to a 1, there's a period of transition that we call the bounce. What we're saying is that if a switch bounces, it'll settle in less than 20 milliseconds. So what we've done is we've implemented a circuit as documented by the truth table on the right side that waits for the input to be stable for a minimum of 20 milliseconds before it switches the output. And the same thing is true. When the input switches from a 1 to a 0, it's going to bounce. We wait at least 20 milliseconds to turn off the debounce signal. What many of you, when I asked for documenting the state transition diagram, explaining it, many never mentioned tick. Tick is the key to make this whole state transition diagram work. Our circuits are running at 50 megahertz, 100 megahertz without the ability to keep track of quote-unquote real time. Here we have a requirement minimum 20 milliseconds. So how did we design our debounce to be able to consider tens of milliseconds? We have a pulse train called tick that occurs one clock every 10 milliseconds. That is a key element to making the whole state transition diagram work. With the tick signal, now I know I have certain elapsed time through my debounce. And it turns out, and this is also something you should be clear about, there's two possibilities. One is that the input switches just before a transition, or the tick switches just after the last transition, or it switches before. In the end, it means that there is a tolerance. There is a period of time that we can't control that we know it will take our circuit to respond. What is that time? The time is It could take as much as 30 milliseconds minus 20 nanoseconds, or it could be as fast as 20 milliseconds plus 20 nanoseconds. Nothing we can do. You could speed up the tick perhaps to 5 milliseconds. You would double the number of states in your state machine. This is a happy solution, I believe. We all should understand what's happening inside of the debounce algorithm. Engineering units, you guys. We should only be communicating with engineering units. You should feel comfortable with engineering units. So kilo 10 to the third, mega 10 to the sixth, giga 10 to the ninth. Tera's now in our vocabulary. You could buy a terabyte drive. I agree, peta is not, but hold on to your hats. It won't be long until you have storage devices that have petabyte capabilities. So that will enter your vocabulary. Then above that, they refer to as exabyte. Going the other way, we have nanos, picos, femtos, atto. All of these you should know. And you should know how to move between them. You should know how to express numbers. Don't give a frequency as 0.002 seconds. That is not engineering notation. We are being trained to be engineers. Use engineering units. And this is just a little chart to talk about how to move between frequencies and periods and the engineering units. I would suggest if you're having difficulties, linger here. Make sure you understand what you're looking at. On the right, what I'm trying to show you, so if I say, what is the period of a 40 megahertz signal? You should know 4s go with 2 5s. You should never write anything other than a 2 5. So 40 megahertz turns out is 25 nanoseconds. But 5s go with 2s, 10s go with 1s, 2s go with 5s, 3s go with 3s. All of this should be in your repertoire at this point in time. So here's an example from our exam, just showing how you can determine the number of clocks in a certain period of time. Once you've determined the number of clocks, you're then able to determine how many bits. We should all be able to do this. If you have any trouble, linger here and look at this till you understand it. And this is just a note. 2 to the 10th is 1K, 1024. 2 to the 20th is 1K times 1K, which is a million. You should know that. And so if you have a number 500,000, you should know, oh, that's a little less than a million, half a million. And since I know that a million is in binary equivalence is really more than 1000, I'm fine. So if 2 to the 20th is a million, I know 2 to the 19th is half a million. Doesn't require a lot of consideration, but it does require you to understand the tricks of the trade. You should, at this point in time, by your junior and senior year of your engineering study, these type of concepts should be in your grasp. This is the we get. In this case, what am I showing? I'm showing that because we knew there were 19 bits, that means the data path is 19 bits wide. We have a comparator that compares to 499,999. Why did I do that? Because if I put 500,000, since I started 0, I'm really counting 500,001. By having 499999 as my terminal count, I guaranteed I have exactly my desired period of time. This is one discrepancy between myself and Pong. I'm okay. If we say we need a signal that is 10 milliseconds, it should be exactly 10 milliseconds. Then we write the Verilog to generate it. This should be within our repertoire. We've done this too many times. When you're given a simple description of a circuit, you should be able to implement it. You're not always guaranteed the circuit description is going to be written in perfect form. You need to be able to break it down to make sure you understand. You know, since it has a 16-bit counter, you know it's an array of flops, so you know there's going to be synchronous device. It refers to a load. It refers to a 16-bit input to load. So before you start drawing the Verilog, you should draw the top-level block diagram. So I know I have a reset, I have a clock, I have up, high, down, low. Sometimes I count up, sometimes I count down, sometimes I load. And if I load, I want data to load into my counter. Now, you should be able to infer at this point in time that the precedence of the load is higher than the count. And I think we'll talk a little more about that here. When you write the Verilog, by looking at the reset input first, what you're doing is giving precedence to reset. What you look at next, you're giving precedence in the synchronous world to it. Here, it really doesn't make sense to count up or down, then look at load. The only thing that makes sense is if I want to load this guy, I do that immediately. If I'm not resetting and I'm not loading, therefore I know I'm counting, and then it just is a matter of whether I'm counting up or down. Keep in mind, if you say if load, don't say then else if not load. It's assumed. If it's load, it'll take the load path. If load is not active, it'll take the else path. Don't complicate yourself in your writing of the code by looking for the opposite sense. So if you say if load else, you know when you get to the else, load is a 0. So at this point in time, I would like to excuse my 360 students, and then I invite my 460 students to stick around. So in our flow, I've stressed this several times, but there are 3 verification steps. There was the block level, the chip level, and the logical equivalence checking. The first, the designers write their own test benches and verify by simulation that their designs work. The second is after all of the code has been integrated together, we then want to simulate the design from the top, in which case we use a test bench that an independent team has written. It's the top level is really the critical verification. So we use a top level test bench to verify the correctness. Still simulation. Once it works, what we have is we have the Verilog code that we've integrated together that we've simulated. We now take that Verilog code, which we refer to as the golden Verilog, and we synthesize it. In the Xilinx world, we generate a bit file, or we map it to gates. What we have on the output of that is a representation of our design, this time comprised of library elements from the target technology. The question is it the same? In the past, people simulated it, but it turns out to be very time consuming. The methodology we're talking about in this class is the third and final stage of verification is we need to verify that the transformation that has occurred through the synthesis process has not changed the structure of our design, that logically the code is the same. To do that, we use a tool that does a mathematical analysis of the resultant netlist in comparing it to the golden Verilog. That tool is not a simulator, it's an analysis tool. And sometimes they require a little bit of hand holding, but once you get it, they're nice. They tell you that the synthesis tool has not changed the functionality. They tell you that the synthesis tool has generated the same logic that went into the golden Verilog. It's the static timing analysis that verifies the timing of the resultant netlist. The logical equivalence is the verification that the resultant netlist corresponds to the golden Verilog that was used to produce the netlist. Verilog, I was surprised here that not everybody could answer this crisply. Verilog is a general purpose digital modeling language. If you have any clouds at all, visit the quick Verilog presentation on BeachBoard. This slide points out that of all the Verilog constructs, which are meant to support designing with ECL, CMOS, TTL, board, chip, that since we have a particular arena we're playing in chip design, specifically FPGA design, we use a subset. That subset is referred to as synthesizable constructs. The rest of the language is available to us in our test bench design, primarily because we don't synthesize it. We just simulate it. But everything that goes into our chip design must be able to be mapped to gates. That is why we restrict ourselves to the synthesizable constructs. That is why I'm so strict when I tell you how to write your Verilog. The operators we went through earlier, if you were with us, I was very surprised. The majority of the 460 class was not able to perform what I consider to be very rudimentary operations. My recommendation is fire up the simulator and play with it for 20 minutes. Type some equations, run the simulator, see what the results are. Just to convince yourself what is the difference between logical operators, bitwise operators, what an exclusive OR is, what the reduction operators are. We'll use the reduction operator immediately on the design of our UART. The reduction operators are referred to as unary operators. There's one operand, and an unary or bit reduction ands all the bits together produces a 1-bit result, or all the bits 1. So I was somewhat disappointed here, but by putting together this presentation, I'm hoping you take the time to walk through and understand it. The trammel blaze, what I present in class, I expect you to know. I know you have a lot going on, but at this point in time, I'm appealing to you. Don't blow me off. Don't ignore what I'm presenting. The whole point of this is that we have a tool that works easily. I know it's been a little uncomfortable to get to where we're at, but believe me, the utilization of the PicoBlaze was uncomfortable. This at least fits in our world under Windows 7, 8, 10. It all works. Um, so I'll let you read this, but you should know what we're doing. As far as the PicoBlaze, the interface timing, the Trammel Blaze is a 16-bit emulator. I've been telling you guys, you want to understand how it operates, study this document. There's the architecture. I'm about ready to add the scratchpad RAM. My scratchpad RAM will have 256 bytes. Actually, not bytes, 256 16-bit words. So we'll increase the instruction set. But from this slide, what I want you to pay attention to is that some of these port ID, outport, import, interrupt, those are the ports of the PicoBlaze that you will use to interface to the rest of your design. It's your responsibility to understand how these work. All of the engine that was presented here, you really don't need to care about, only if you're interested. All you need to care about is how you interface to the world around you and how you make it do what it's supposed to do. How you make it do what it's supposed to do is using the instruction set. And my instruction set is very similar. Perhaps I need to apologize. Let me publish my exact representation. I'm using the terms contained in the parentheses. But I need to publish that so you can get that. But the document shows you how every instruction operates, and if the flags, the carry or the zero flag, are going to be set. Whenever there's a question mark, that means it's determined by the result of that operation. If it's a 0, that means it'll always be a 0. If there's a dash, that means that instruction will have no effect on the 0 or carry flag. The timing on the interface, which most people were not able to do, which I have been trying to encourage you to learn, is captured inside that spec. And basically, why is it so important? Because you need to interface to the PicoBlaze. So you need to know what signals are going to tell you what coming out of the PicoBlaze in order for you to receive the data and present the data to the Trammel Blaze. So in summary, it's a 2 clock operation. On an input, the first 2 clocks, the port ID has the address that we're trying to read. It's expected then that you respond once you see the read signal with the data that the processor is asking for. And then following clock 2, now that data is inside of the processor in the register that was designed as the target. You'll find a similar slide on BeachBoard for the output. So that's it. And I know it's a long presentation. Hopefully it'll fit on YouTube. Please take the time to walk through and make sure that all these rudimentary concepts are in your understanding. And hopefully we'll have a great last part of the semester.